Our next speaker is Ioannis Diamantis with a talk titled Bonded Knots and Braids, from Topology to Algebra and Protein Structure.
Thank you so much for having me here. So I'm Ioannis Diamantis, and I'm going to talk about bonded knots and braids. This is a joint work with Professor Louis Kaufman from University of Illinois at Chicago, Professor Sofia Lambropoulou from National Technical University of Athens, and Dr. Sonia Mahmoudi from Tohoku University. So let me go through a little bit what I'm going to talk about today. So I'm going to very briefly introduce classical knot theory. And I'm just going to introduce what a knot is, what we need from classical knot theory in order to continue and introduce the new concepts that we propose, which are bonded knots. And this is the part which is a joint work with Professor Kaufman and Professor Lambropoulou. Then go to bonded braids, which is joint work with Professor Lambropoulou. And in the end, time permitting, we'll see. I'm not sure if we will have the time to talk about bonded diptytangles, which is a joint work with Professor Lambropoulou and Dr. Sonia Mahmoudi from Tohoku University in Japan. All right, so what is a knot? Most of us are familiar with knots. A knot is just an bending of the circle S1 into R3, or the compactification of R3 S3. And here we can see some very classical examples. The unknot, which is the simplest knot that exists without any type of crossings. The trefoil knot, which is the simplest knot with only 3 crossings. And here we see 2 links, which are nothing but bendings of K copies of S1 into R3 or S3. Here we see the Hopf link, which consists of 2 components, and the Borromean ring, which consists of 3 components. All right, so we need to be able to understand the difference between 2 knots. We need to be able to distinguish 2 knots. And for this reason, we introduce in geometric topology, we introduce what we call isotopy. So, and in this example here, you can see that we allow knots to be, let's say, flexible, and we can deform them in space without cutting and pasting. All right, so you can see that this monster here initially, if the animation will work, this monster initially looks very complicated and knotted, right? But with some very, very, very simple deformations of the space, you can show that this is nothing but the unknot. All right, so this is what we call isotopy. These 2 knots are called isotopic. In other words, there exists a continuous orientation preserving homeomorphism that takes one knot to the other. So whenever there exists such a homeomorphism, we will call the 2 knots isotopic. But this is kind of complicated in 3 space. So to simplify things, we consider projections of knots onto diagrams. So onto a plane, and this gives rise to what we call knot diagrams. So what is a knot diagram? It's nothing but a projection of a knot onto a plane, right? But it has to have some restrictions. For example, we only allow finitely many double points, which we will call crossings, as you can see here, right? With this extra information, which strand goes above the other. So we call that under-over information. So a knot diagram, we start by having a knot in R3, let's say, and we project it onto a plane, keeping in track which strand lies above the other. But of course, we can see that we simplify, of course, our life by having diagrams. But of course, we can see that everything depends on the projection, on the plane that you consider to project your knot on. So we need to translate isotopy in terms of knot diagrams. And this was done by Reidemeister like 100 years ago almost, where Reidemeister proved that 2 knots are isotopic if and only if corresponding diagrams of theirs differ by a finite sequence of the following moves. So we have the Reidemeister 1 move that you see here, which is a twist, right? A kink, a positive or negative. So you create a positive or a negative crossing here. You have, which means under over positive negative. You have the type 2 moves, right? Where you can see you have 2 strands and one can go below the other or above the other, of course. And the type 3 move, which is usually called slide move, because you can see that one strand can travel from one side of a crossing to the other. Of course, these 3 moves together with planar isotopy gives rise to isotopy in R3 or S3, let's say. This is how it is translated to be exact. If we exclude Reidemeister 1 move, if we exclude this move, then the resulting equivalence is called irregular isotopy. All right, and that's going to be very important for us. So we have two different types of isotopies: irregular isotopies, which means that two knot diagrams differ by Reidemeister 2, Reidemeister 3, and of course planar isotopies. And we also have what we call ambient isotopy, which involves regular isotopy together with the extra Reidemeister 1 move, the positive or the negative kink. All right, so this is actually what I will need from classical knot theory. And what we will propose is a model to try to analyze proteins, as we will soon see. Okay, so this is what I got from Wikipedia. What is a protein? So according to Wikipedia, proteins are large biomolecules and macromolecules that comprise one or more long chains of amino acid residues. So you can see here, right, a figure of a protein. So we understand that proteins are extremely important for life, right? Because they are responsible for many, many, many different things in life in general. And what is extremely important is that back in the 90s, it was assumed, it was conjecture, and later confirmed that some proteins actually exhibit some knotted topologies. And in fact, about 1% of, let's go here, about 1% of all proteins, all known proteins in the protein data bank are now known to be non-trivial knots, to contain non-trivial knots. And what we actually also conjecture, right? It's not written in stone, but we believe so. This is true, that the type of knot that the protein forms actually, let's say, may enhance a molecule's stability. In other words, it gives us information about its thermal and kinetic properties, let's say, which means that being able to model and analyze the knots that proteins form becomes extremely, extremely important, not just from a mathematical perspective, but also for biologists and chemists, I would say. Now, how would we try to model these knots that the proteins form? So to analyze that, one common approach is to artificially close the twin points. This is called the direct segment closure. So you connect the twin points because, as we mentioned before, they are open. Proteins are open biomolecules. So we can connect artificially the two endpoints and form a knot. And then you can actually study knots because we know how to study knots. We have invariants to tell us whether a knot is equivalent to another. We know we have lots of information that we can actually use here. But as I said before, this is a little bit artificial. So you force a closure, you form a specific type of knot, and you get some information. But lately, the last 10 years, Turaev proposed a completely different method. Turaev proposed the concept of knotoids. And what are knotoids? Knotoids are open knots. So imagine that you have a knot, you cut it somewhere, right? You get rid of the arc that you cut, and you have an open-ended knot diagram now, with the two endpoints usually lying in different regions of the diagram. So this is extremely important because it makes perfect sense to try to study proteins using the concept of a knotoid, because knotoids are, you don't consider this necessarily, you don't consider this closure. And I'm gonna show you in a minute how important knotoids are, because they are really related, very close related to classical knots. All right, so we have to also remember a couple of things here, that the endpoints are allowed to move freely in the region that they belong to, but there are some forbidden moves that you can see here. So you cannot take the endpoint and push it into a different region. All right, because if that was the case, then every knotoid would be unknotted, would be a trivial knotoid, an arc. All right, so how knotoids are related to classical knots, this is very interesting. So Turaev also proved that the set of knotoids you can have a surjective map from the set of notoids to classical knots. So what does that mean for us? For us, it means that invariants of classical knots can also be computed on notoid representatives. So this is very important because, as I mentioned before, we have lots of different invariants. Some are strong, some are not as strong to distinguish knots. But moreover, there is an injective map between the set of classical knots to notoids, right? So, and this means actually that the theory of notoids is nothing but a generalization of classical knot theory, or an extension, if I may say. All right. So notoids, we understand how important they are in order to study these proteins, and we will go to that a little bit later. Because before that, I want to just explain, just make sure that we understand one simple thing, that proteins you can actually study proteins by notoids, or if you like by knots, but there is some extra information that we need to keep in mind. And what is that extra information? The information is that the proteins also include what we call bonds, right? And these bonds link parts of the notoid, of the protein, or of the peptide backbone. So these bonds are going to be extremely important to us, because we are trying to model notoids by simplifying the concept as less as possible, let's say. All right. So we need to find a way to include bonds into the theory of notoids, or into the theory of knots. So, oops, sorry. So we define what we call a bonded link, right? So we define a bonded link to be a classical link. Here in this figure, you can see this black curve forming a link. Sorry, the black curve is a classical link, and in orange, we have what we call bonds. So what is a bond? Is nothing but an embedded arc into the complement of that link. All right. So the only thing that is important here to keep in mind is that we allow bonds to intersect. We allow bonds to have to be knotted. We allow bonds to have to have crossings between bonds. All right. And this is a completely new approach that we believe is very, 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 very important in order to be able to actually analyze and study the proteins. Okay, so this is what we call a bonded link. And now what we want to do is we want to actually be able to explain, to describe isotopy of bonded links. So in order to do that, first of all, we want to understand how bonds may behave, right? So this comes from like 40 years ago, from Conway and Kaufman, from the theory of embedded graphs. So we will take for granted some things that we know that are true for embedded graphs, and we will try to see how we can actually generalize them for bonded links. So here, if you forget the colors, if you forget that bonds are embedded arcs in the complement, and you can see this monster here, you can see it as a graph, a trivalent graph, actually, a special case of a trivalent graph. And this is extremely important, because using this fact, we can actually have invariants of bonded links by adapting a little bit the difference between an embedded graph and a bonded link. So let's start first of all by describing isotopy. And of course, what we are trying to do here is generalize Reidemeister moves for the bonded link diagrams. So we have here all possible moves that are allowed. In our case, this is a beautiful theorem that we proved, and we have all the moves. I'm going to show you all the moves that are allowed in our case. So, of course, we have the planar isotopy. So, an arc, a classical arc. By classical arc, I will mean an arc of the knot, can actually form what we call a delta move. But this is something that we allow bonds to also satisfy. And of course, there is this arc, the classical arc, that contains a bond, right? That contains the endpoint of a bond. And you are allowed to also use planar isotopy for these kind of things. All right, so that's one thing. Now we go to the classical Reidemeister moves that we allow. We showed before the Reidemeister 1, a positive or a negative king. Reidemeister 2, where the two strands can form, can go above the other or below. And the Reidemeister 3 move, where you have one strand passing the other side of a crossing, positive or negative crossing, from above or from behind, there's no difference. So all possible situations between the crossings here. And the same moves we allow for bonded arcs. And that's something very new, I would say. No one has considered so far that the bonds can actually be deformed. All right, so we start with a very general case, and we allow bonds to have to be, let's say, a little bit more elastic and be able to deform them. So we are trying to model this deformation of the bonds, and we start by simply saying that you are allowed to have the classical Reidemeister moves, but now for bonds. And next, we need to see how bonds behave when they meet, let's say, a classical strand. So we can see here that if we have a classical strand and a bond, we can form a Reidemeister 2 move, right? Or we can form a Reidemeister 3 move when you have either two classical strands and we want to pass the bond to the other side of the crossing, or if you have two bonds forming a crossing and you have a classical strand that you want to pass to the other side of that crossing. So these are Reidemeister 2 and Reidemeister 3 moves respectively, but with all possible cases, bonds or classical arcs. And we have one extremely important move for us that we call the vertex slide move. And this can, again, have all possible situations, bonds or classical arcs, where you can see, if we look at the left-hand side, you have a classical strand with a bond, right? And it's like a finger move. You can poke it, right? And you can form a Reidemeister 2 move here, but that move also involved another bond. So the end point here of the bond can pass through the other bond. All right. And of course, it could have been the case that you only have one bond and two classical arcs, and you can do the same. So this is a very important move for us, and we will come back to that in a minute. But as you can see, I haven't involved so far, right, the Meister 1 move for bonds. All right, I haven't included Reidemeister 1 move for bonds. And remember, I have only included Reidemeister 1 when you have only one bond. So if we go here, we can see the two different types of equivalencies that we will introduce and we will discuss today. First is the topological vertex twist that you see on the left, where you see in the middle, you have the bond, right, being attached to two standard strands. And we show here that it is allowed to form a positive or a negative crossing, to have a Reidemeister 1 move on one of the two classical strands of the bonded link. If this is the case, this is called the topological vertex twist. But everyone so far have studied bonded knots considering that they form a rigid vertex, right? So if you want to do a kink on the one side, then the bond, right, will create an additional kink to the other side. And this is called a rigid vertex twist. So we introduce here what we call a topological vertex twist, where one strand is allowed to perform a Reidemeister 1 move and the other not. And this is going to be extremely important when we study bonded braids. And the reason why we have that is this. And we will distinguish from now on the bonded links into two categories. Let's say those subjected to topological vertex isotopy, we will call them topological bonded links. And those subjected to rigid vertex isotopy, we will call them rigid bonded links. So there are two types, rigid and topological vertex isotopy, let's say, vertex bonded links. These two differ only by these two moves. So if you insist on having rigid vertices, then you have the rigid bonded links on the right that you see here. But if we allow bonds to be a little bit more flexible and not rigid, then you can have moves that look like this one on the left, where the Meister 1 move can be performed either to the left or the right standard strand. Okay, so now what we have is two different categories, and we would like to see whether we can have invariants for these two categories. And actually, we do. sorry, before that, I forgot to mention that there are some important forbidden moves that we have to keep in mind, right? For example, if you see here, if we have an arc engulfing and embracing a bond, you cannot just get rid of that and push it down. All right. Of course, it makes perfect sense, but there is another category of links called tight links, where the bonds that we call ties are not embedded arcs, which means that they are like ghosts. You can do this move. So this is also a very a difference between tight and bonded links. And you can see here it's exactly the same thing, but in a more braided level. So this bonded here cannot slide through this strand because of these two crossings. Okay, and the other thing which I think is very important to keep in mind is that the endpoints cannot interchange. All right, and they cannot cross, as you can see here. You cannot slide this endpoint A behind or below B. All right, these are forbidden moves. Of course, these are some of the forbidden moves. There are infinitely many forbidden moves if you want to be exact, right? Positive crossing cannot become negative, etc., etc. But these are very important in the sense that they are. We only focus on the bonds because we introduce the bonds and we want to see what things are allowed and what things are not allowed for bonds in our category. So now let's discuss a little bit invariants. So one extremely simple invariant is called the unplugging, and this invariant was due to Kaufman, if I remember correctly. I don't remember. I think it's only Kaufman, correct. So what he did is the following. He considered the trivalent, as you can see here, he considered our vertices to be like graph, right, for graph. And then he performed all possible unpluggings that you see here. Okay, and every time he considers an unplugging, he creates a beautiful knot or link, a classical knot or link, right? But because he considers for each and every trivalent vertex, he considers all possible unpluggings, he has a family of knots and links. All right, so this family, the set that they form, is actually an isotopy invariant for our standard bonded link. Okay, and which means that since you have standard knots and links, you can compute any known invariant for these standard knots and links, like from polynomial invariant to anything you like, and this invariant will remain invariant, right, for our bonded link. So that's the first thing, which I believe it's very, very, very interesting. And we are talking about the topological vertex category. If you want to see the rigid vertex category, we would do the following trick. We will take our bond and replace it by a band. And then within that band, you can insert any tangle that you would like, anything that makes sense. Two crossings, anything that you would like. And of course, by doing that, you form again classical knots and links. So again, the same idea, the set of these classical links that derived from all possible tangle insertions that you can consider is a rigid vertex isotopy invariant for our bonded link, for our initial bonded link. And similarly, any isotopy invariant for for these classical links actually is an invariant for our bonded rigid vertex bonded link. So these are known results, right, that we actually adapted in our two categories. And now we go a little bit further because our initial intention is to form braids, right, and discuss bonded braids. So the next thing that we do is we consider what we call an intermediate category, the regular bonds, the irregular bonded knots or links. Okay, so what's the difference between bonded links and regular bonded links? The difference is that the bonds are not allowed to form knots anymore. All right, so they are not allowed to form knots, and they are not allowed to have self crossings. Okay, so let's see, no crossings in general, right, between bonds. Okay, so an interesting proposition suggests that any bonded link, either topological or rigid, doesn't matter, can be transformed isotopically into a regular bonded link, as you can see here. And we do that using the the vertex slide move, the poke move. All right, you can see here that if you start from this, you start unknotting. right? You go through the whole thing, you knot it, and then you are left with a bond that has no crossings between, it's not self, right? It doesn't form a knot anymore, and it has no crossing, so it's free of crossings. So this is the regular category where, of course, all the invariants that we mentioned before still hold for this category. And the one that we care a little bit more is try to understand again the Reidemeister moves, right? The equivalence between these two. And you see here all the moves that are allowed. As you can see, what is excluded are the moves that would take our diagram, our regular diagram, into not being regular anymore. So we have two regular diagrams, and we want to see the moves that you are allowed to use in order from one to go to the other without leaving the category of regular bonds. And these are the moves. As you can see, as before, we have the vertex slide move, right? You have what we call mixed Reidemeister moves, which means standard strands and bonds. And here you can see that we are using the rigid vertex. Of course, you could use also the topological. It depends on what you want. Here is the topological. Here is the rigid vertex isotopy. All right. And finally, we go to the last category, which is the most important one, the category of tight bonded knots. And this category is very important because it will allow us to go and define bonded braids. So here, the bonds are completely free. The region of a bond is free of arcs. There are no other bonds, of course, as in the regular category, but now there are also no other classical strands in the region of a bond. So the bond is like a line segment, which is completely free. There are no arcs in between the two endpoints of a tight bond. And of course, any regular bonded linkage diagram can be transformed into a tight bond link, as you can see here with the poke move, with the finger move. And here are the topological isotopy moves that you're allowed to use the moves that you are allowed to use in the topological vertex category. And of course, if you replace the top move with the rigid vertex, you have the rigid vertex isotopy moves, that category. Okay, so this is extremely important so far for us. And now you can go and define any invariant that you like by using any method that you like. For example, in this particular case, I show you a very naive generalization of what we call the bracket polynomial, where if you exclude the first rule that you see here, the three rules are the rules that are used for the classical Kaufman bracket polynomial for knots and links in R3. But here, we also keep track of how many bonds a tight bonded link had. All right, so whenever you have a bond, you replace it, you get rid of the bond, and you introduce a new coefficient, let's call it B, and the number of B's will just correspond to how many bonds you have. Very naive approach, because if you have 2 or 3 bonds in different regions, behaving in a different way, this will not capture it. But it's just a way to show that we can actually generalize any invariant that we know into the category of bonded links in a simple way. All right, not the best possible way, maybe, but in a very simple way. And now we go to braids. And I think I have some time to talk about braids, and I will not talk about the DP tangles, unfortunately. So braids are nothing but classical links, right, that are organized, that have an organized boundary, right? So imagine that you have 2 bars, top and bottom, and you enumerate the strings that you have, and you have strictly decreasing strands, right? Strictly decreasing strands that tie the 2 bars together. So that's a beautiful braid. And there is a natural orientation from top to bottom. Now, Alexander proved that any knot or link can be represented as a closed braid, right? And the closure operation is the operation that I show you here. Okay, so this is isotopic to a bonded link, and every bond, every knot or link can be represented as a closed braid. So with Professor Labropoulou, we proved the analog for bonded links. But before I go there, I want to say the following. Let's do a recap so that we get a little bit the idea of what we want to do. So we start with a knot in S3. All right. We take a diagram of a knot to simplify our life, of course, and we express isotopy in terms of on the diagrammatic level with the Reidemeister moves. Then we open the knot and we consider braids. Okay, and we know that the closure of a braid is a knot, and any knot can be represented as the closure of a braid. So now the next step would be to translate the Reidemeister moves, right, the isotopy, onto the level of braids. And this was done by Markov with these two beautiful moves: conjugation, where you can interchange two braids, right, and stabilization. So you can add an extra strand in the end that forms a positive or a negative crossing here. All right. Then Artin proved that the set of braids actually forms a group, the Artin group, right, the braid group, which has, sorry, the generator sigma i's that you can see here, and the operation is just concatenation. You just take one and put it above the other, right? That's the multiplication in this set, in this group, and then Jones in '84 said that instead of studying knots up to Reidemeister's theorem, we can study braids up to Markov's theorem. And he got the Fields Medal for that, actually. What he did, he constructed the Hecke algebra. He considered the Hecke algebra, which is nothing but, you can see here, the group algebra CBN, the classic BN meaning the classical braid group, over the ideal generated by this quadratic relation, sigma I squared equal to q minus 1 sigma I plus q. And using a using the Ocneanus trace, which, as you can see here, a unique Ocneanus trace, as you can see here, each one resembles the two moves that Markov proved that suffice to describe isotopy, right? And he constructed the Jones polynomial, and later on the two-variable Jones polynomial known today as Hopflik. And this is exactly what we want to do. We want to take our braids, bonded braids, and try to study the algebraic structures underneath, behind that. Okay, so just to conclude, what is a bonded braid? Is nothing but a classical braid that also involves bonds that we mentioned before. All right, we have the classical closure operation. We don't change anything here, and we prove that any bonded link can be represented. Sorry, I can go here. Can be represented as a bonded. Oh, I forgot to add it. Sorry, my bad. Any bonded link can be represented as the closure of a bonded braid. And then the next thing would be to try to understand a little bit Markov's theorem, right? We have to understand how we can adapt Markov's theorem here, and we have done that also. I don't know if I would, I will not have the time to discuss that. But what I want to discuss, I'm sorry for this, because I see that I don't have much time. What I want to discuss is the following. The most important thing, and this is I would say the conclusion of today's talk, is that you can actually turn into a bonded braid any topological bonded link. Unfortunately, not any rigid vertex, not any rigid vertex bonded link. And this is because if you have two strands that are oriented they have opposite orientations, antiparallel orientations, then using the classical topological bonded link isotopy, you can just form a Reidemeister one move and change the orientation of this guy here to be downwards, right? Because remember, braids have a natural orientation from top to bottom. Okay, and if you have both going like oriented upwards, if you have both strands, you can just form topologically again isotopy on the left and on the right, so that they will go downwards. And then for the other strands, you use the classical Alexander theorem, the classical results of Alexander theorem, and you can braid them. But if you have, this is not true in the rigid category. For example, on the right-hand side, you can do that, but on the left-hand side, there is no way that you can turn this into a braid, because you are not allowed to use a Reidemeister one move only on one of the two strands. And that was one of the things that we proved together with Professor Sofia Lambropoulou in this concept. Finally, I just want to mention that the bonded braid, the set of bonded braids do not form a group, they form a monoid, and this is because the bonds are not invertible, all right? But if you allow, I will go here, if you allow the inverse of a bond, so we call that enhanced bonds, which means that we assume that bonds are equipped with, let's say, some type of forces, right? Some type of a force, either attracting or repelling forces. So we have two types of bonds. Then we can actually consider the enhanced bonded braid group. And with Professor Sofia Lavropoulou, we proved that the bonded braid monoid embeds into this bonded braid group, enhanced bonded braid group. So to conclude, I will skip the Markov theorem because I want to conclude that whatever we said is also true for bonded notoids, and this actually is a little bit a better way to model proteins. And we proposed also a very, very, very interesting type of closure, how to close a bonded notoid. We call it the bonded closure, as you can see here, which is again something completely new. We connect the two endpoints, but not with a classical arc. We connect it with a bond, and this was actually inspired by Young and Mislow, a paper of Young and Mislow, like in '94, where they actually did something like that. As you can see here, the pictures show exactly this. Although they don't call it bonds back then, they didn't call it bond, they called it something else. They didn't call it a closure. So, and we were able to prove some very interesting results, and hopefully a paper will be available on archive soon. So I think I should conclude, right? I don't think that I have more time, but
You have 5 minutes more.
oh, perfect, perfect. If I have 5 more minutes, I would like to discuss a little bit the doubly periodic tangles and tangloids.
Great.
So this is again something extremely important because what we are trying to do is we are trying to use bonded links and bonded braids to actually, sorry, bonded links only, to actually try to model some other type of how can I say it nicely, other type of things. For example, textiles. We're trying to model weird things, phenomena that happen in nature that we would require a repetition of our tangle, of our link. So what are we talking about here? We are talking about, I want to go straight forward here. We are talking about something very, very, very different. So we consider now linkoids or notoids, right? Let's focus on notoids for a while. We consider notoids, but now they are not embedded in S2, but we consider them in, as you can see here, in the thickened torus, right? On the thickened torus. So you have a bonded linkoid, a bonded notoid, sorry, in the thickened torus. So we cut open our beautiful thickened torus. We cut it open, and we have what we call here a flat motif. And a DP, a doubly periodic tangloid, would correspond to considering this monster here repeating itself infinitely many times, top to bottom, left, right, in two different directions. So what you create here is what we call a doubly periodic diagram, right, of our DP tangloid. Now, of course, again, here things are very, 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 very tricky because now we are not in S3 or in S2. We are in the thickened torus. So there is a very, very interesting diagrammatic approach to that we also introduced in our paper. But I want to emphasize on the fact that a simple move that happens somewhere, classical Reidemeister move that happens somewhere in here, will happen everywhere, will follow everywhere. And that's what makes it very, very, very interesting and different. Of course, for DP tangloids, there are many things that one needs to discuss. For example, what kind of closure can I have? We saw before that there are types of notoids that you can actually, you can close a notoid, sorry, to form a knot. Can you do the same thing here? And are there different types of closures as we saw for our bonded links? And the answer is yes. There are different types, and we are currently trying to understand what these different types would mean. Example, if you see this picture here, the flat motif that we say, you can have a direct segment closure here, right? Or you can take this, go to the other side of the torus, or up, down, it doesn't matter, and connect it again. And you might wonder, why would I do that? It would maybe I create more crossings, so I make things more complicated. The answer is that maybe you are actually you are unknotting it without understanding. So we don't really know what's going on here and what is the best possible approach. And this is under investigation at the moment. So I just want to say, well, no, I think that I should stop here and not go into more details regarding this. You can find papers on archive on dipetangloids and dipetangles, and I hope that pretty soon we will upload the paper on bonded knots and bonded braids on archive too. So thank you so much for your attention and for having me here.
Yeah. Thank you very much. It was a very insightful talk, very great presentation. It's a pleasure to have you on this conference.